Here we go.
Here we go. Good. Right. Okay. So good evening, everybody, and welcome to the August OREF meeting. I'm delighted to welcome Sarah. Is it Sara or Sarah?
Sarah.
Sarah. Yeah, I did ask you that before and I forgot, so sorry for that, Sarah. Welcome Sarah along, who's the director of EPSRC National Centre for Energy Systems. So I'm not going to steal her thunder, but Sarah very kindly agreed to come and talk tonight. She's on the industrial advisory group that we've set up as part of Reflex, so she knows a bit about Orkney, and we're really looking forward to hearing about what can be done in terms of energy performance in some commercial buildings. So we don't have many commercial buildings here, but we do have some, and it's an often overlooked area. So the plan is, Sarah, if you're going to talk for a half an hour or so, then take some questions, and then we see where we go after that, if that's all right with you.
Yes, that's great. Am I okay to share some slides, please?
You certainly are. You have control. You have the floor.
Okay, can I ask the host to enable screen sharing?
There's lights just on that, I think. So let's see if we go.
You should be able to share now.
Yes, that's great. Thank you very much.
We're seeing that, Sarah.
Great. Okay. So thanks very much for the opportunity to chat to you today. I'm going to say a bit about a project that we've been running at Newcastle called Building as a Power Plant. And as Neil said, this is a study to look at the potential for operating a particular building in a way that is offering flexibility to the local energy network, in this case, electricity, but I'll explain why it's electricity. So as with any good project, it's not just one person. So I would like to give credit to my colleagues here. So Harris Patsias is an electrical engineer who supported some of the work looking at the local electricity network. Mohammed Royapur is a building services engineer who did a lot of the building modelling work here. Pete Davison does work on energy markets, and so was the expert from the point of view of the value of some of the services that this building could offer. And Mehdi Pazuesh did work on data analysis, particularly data quality. So he was our go-to person when our data had missing values and we didn't know what to do with that. So it was a real team effort here. And so what we wanted to do was take a look at the potential for buildings to offer something to energy networks. Generally, in terms of the potential energy use of buildings, then we're looking at something like 20% of all global energy demand in order for us to operate buildings. And in terms of International Energy Agency member countries, which tends to be a lot of European and countries with quite well-developed electricity and energy networks, then up to 40% of energy consumption is in relation to what we do in buildings. And particularly in the UK, we're quite interested as researchers in buildings because we know that there's a need for decarbonisation. We know that there's a need to get more renewables and more storage into our systems. We know that reliability and resilience of our energy systems is important operationally. And we also know that the electricity infrastructure needs to start thinking about increasing demand for electricity to service heating and to service electric vehicles. So if we look at where energy is currently getting used in the UK, then the red line that's hovering somewhere between 100 and 500 here towards the bottom of the scale is our electricity demand. in the UK. It's a bit seasonal, so you can see it peaks a little bit more in winter and drops over the summer. But the blue line is much more seasonal, and that's our gas usage in the UK. And so if buildings are going to be electrically heated, we need to be able to cope with much more variation in demand as a result of shifting from gas to electricity. Some of the other things on here, the blocky grey line is liquid transport fuels. So if that was to convert to be mainly electrically provided, that's another additional demand on our electricity network. And down at the bottom, we've got a green line which shows the contribution from renewables, and partly hidden behind that is the electricity contribution from nuclear. The very high peak around here is our beast from the east that we like to refer to. So even knowing our fairly predictable winter energy demand, there can be even peakier bits of that peakiness between seasons of our heating. So that was the motivation really for building as a power plant. We thought if buildings are going to be heated electrically, then we need to come up with ways of trying to mitigate, reduce the problem of seasonality and the impact that that might have on energy networks. So we started off by looking at a particular building. And the building is called the Urban Sciences Building. It's on a location in Newcastle, very close to the city centre, called Science Central. It's where Newcastle Brewery used to be. And before that, it was a coal field. So we started off exporting coal from Newcastle, then exporting beer, and now we're trying to export our knowledge. And so on the Urban Sciences Building, we've got on the left-hand side of this slide, you can see the schematic, which is the electricity network. And so we've got, in terms of the building itself, Urban Sciences Building, we've got that shown here electrically. It's quite close to another building called the Core on site. The building itself has got some photovoltaics. It's got some energy storage within the building. Close to the building is a energy centre for the site, which includes some combined heat and power. And we've also just commissioned a electric vehicle charging centre, which has a number of fast chargers on the site. So all of these are electrically connected to the distribution grid, and these little circles here represent transformers. So those are the kinds of things that you might see locally on Orkney. So this is just a kind of schematic showing all those different bits of the building. There's quite a lot going on in terms of the electrical structure around the building itself, which is what kind of makes it interesting, because this is the way our city centres might be going, or are semi-urban towns and villages, depending upon how many commercial loads there might be locally. So we've got this building, the Urban Sciences Building. It looks like this from the outside, and it was designed to a particular specification that the university came up with, and we wanted it to be a research building. So everything is probably a little bit over-spec'd compared to a typical commercial building. But the right-hand diagram shows all the services. And so what this building has is a heating system and cooling system, which is electrically driven. So the building has a large number of heat pumps. And the reason there's quite a large number is because we wanted to be able to do some research looking at each floor and being able to control it separately. And also there's 3 zones to the building that we wanted to be able to control separately. So there's a large number of heat pumps. There's some heat meters around the building, so we can measure heat flow between spaces. There's a lot of metering of electrical loads in the building. We've got some water meters in there as well, because we thought for research purposes, it'd be good to know where and why water is being used. And there's also some gas meters. So it's a kind of hybrid in terms of the way that the building is heated and cooled. If we were to build this normally without all of the extra instrumentation and the zoning that we came up with in order for it to be a research project, then this probably would have been more like a 25 million to 30 million pound building, but it came in at about 60 million because of all the additional research laboratories and research facilities just outside the building as well as within the building. So it's a real research tool for us. And because there's so much in the way of metering as well as sensors, the building itself collects data in the millions over the course of a year. So we looked at performance of this building for 1 year, and we were looking at in excess of 4 million data points. So it's also a big data type experiment as well for our computer scientists, who are actually the ones in the building. If you've ever worked with computer scientists, then I'm not going to say they're paranoid, but they certainly know their stuff about sensors and pervasive sensoring architecture and cybersecurity, and they're very concerned about us testing on them. So we have quite a firm ethics process as well. If you want to do any experiments using the building and its occupants, there's quite a firm ethics procedure to go through to do things like turn off the cooling in certain spaces, or ramp down the level of lighting and so on. So in our building then, we have got the opportunity to experiment a bit. We have a heating system with heat pumps. There's several of them on each floor. There's 25 in total in the building. And they are on a wet circuit. So there's water running around the building that the heat pumps step up the temperature of to heat the space, or step down the temperature of to cool the space. And there's some preheating of that water circuit, which is why it's a bit of a hybrid. There are some gas boilers to do some preheating, which wouldn't always be necessary. I don't know why they came up with that design, to be fair. It wouldn't always be necessary in a commercial building to have some preheat. And certainly it wouldn't necessarily always need to be on a water circuit, but by having it on a water circuit, the heat pumps are inside the building. Whereas for some installations, if it's an air source heat pump, it would be extracting air from the outside and would be on the outside of the building. So we looked at some spaces in our building and what we could do in order to do some fancy control, essentially, of the electrical load inside it. And one of the things that we could look at is the ventilation. So it's mechanically ventilated spaces inside. Windows are openable, but there's also mechanical ventilation. So in a typical office space, which is the graph on the left, compared to a worst case scenario, which is the graph on the right. What we've looked at here is our carbon dioxide sensors. So the carbon dioxide is monitored throughout the building. There's tens of carbon dioxide sensors. And the mechanical ventilation is there to ensure that there's sufficient fresh air to keep the carbon dioxide levels below 1,000 in terms of the measured CO2 in parts per million, which is the left-hand axis of the graph. I had to wave my hand there to remember left and right. So the blue bars are showing what the CO2 measurement was like during a period when the ventilation was not on. And as the orange line shows occupants coming into the building, we've got some CO2 sitting at around about 1,000, just under, so 986. And then in terms of our CO2 measurements, we're trying to ensure that the CO2 is keeping the air healthy and fresh and safe for occupants. And so we wanted to look at our fresh air rate when the ventilation is on compared to when the ventilation is off, what that does in terms of electricity saving for the space, but what that also means for CO2 buildup in the space. So we've got blue bars showing that the ventilation is on and the air handling units are on. Then when the air handling units are off and there's no blue bars and we've got some occupancy, which the orange line is showing, then our fresh air rate gradually increases in the space until it reaches this threshold where we can't override the system, the air handling unit kicks back in. So we've got some opportunity to save at times of peak electricity demand, save electricity by turning the air handling units off. But our typical office shows that we can really only do that for 4 or 5 hours in terms of when the threshold is reached. So in a typical office space, CO2 threshold reached after 3.5 hours. When we've got a worst case space, so it's a reasonably small space, we looked at a small office in this case, then the air handling units are on to start off with in the morning. You can see those blue bars. We've got nice air handling unit, fresh air rates happening. We turn them off at 10:30. We see what happens to the carbon dioxide levels, and they rise quite rapidly. In the case of this particular office space, we're exceeding carbon dioxide levels after 30 minutes. So we can only turn off and save and help the network for 30 minutes in that space compared to the more typical office space. So air handling units was one thing we looked at as something we could control differently. And then we also looked at the heat pumps, and we looked at what we could do with the heat pumps in terms of winter, but also in terms of summer, what we could do in terms of turning the heating off or turning the cooling off. And so we looked over 5 months, that's quite optimistic sometimes in some places, 5 months of heating season, but we looked at 5 months, November 17 through to March 18. And what we identified for this is a worst case. What we looked at was if we were to turn the heat pumps off for a period of time, how quickly would the building cool down? And so these bars are showing the extent to which the temperature drifted and how quickly it drifted. So we're looking at the cooling rate. And so what we're trying to do is ensure that the temperature drift does not exceed 0.5 degrees per hour. 0.5 degrees per hour is, according to guidance, the rate of cooling that the human body would notice, 0.5 degrees an hour. We're using Kelvin here, but it could easily be centigrade because it's just a change in temperature rather than an absolute temperature. And so the number of times during which the cooling rate exceeded 0.5 degrees per hour during those winter months, that happened just over 1% of the time. So our building was actually quite slow at responding. It's quite thermally heavy and and it was designed that way. And so for 1% of the time, if we were to turn the heat pumps off, people would notice the cooling effect. Fab. That's a very small amount of time. We also did the same thing looking at if we turned it off in summer and stopped the cooling, how quickly would it warm up? So this is the summertime thermal drift in our worst performing space. We again want the temperature to change no more than 0.5 degree per hour. And we looked at the months April through to August. And we found for that period of time that more than 14% of the hours were experiencing a warming up that was more rapid than that. So whilst people might not notice so much if the heat pumps were off in winter for a short period, they would notice more often if we turned them off in summer and turned the cooling off for a period. So our building is doing slightly better in terms of heating than in terms of cooling response. But what we did find is that in terms of controlling the building differently and helping the local electricity network at times of stress, then we could do that for around about half an hour for carbon dioxide, so ventilation. And we could do that for about 4 hours for the heat pumps without too much effect, I suppose, on people's experience of the building. And what we also looked at was, well, if you've just helped the network by being off for a bit, how quickly does the building recover and then is ready to offer again? And certainly for the carbon dioxide levels, you do need to have the ventilation back on for a reasonable period before you can offer another half hour. And so pre-demand response, so we're calling this thing where you turn stuff off, we're calling it demand response, which Reflex has been looking at. If it's before any demand response event has happened, then we're okay for a 45-minute offer of ventilation turn down. But certainly in terms of restoration, sometimes it can be as quick as 15 minutes, sometimes as long as 45 minutes before we're ready to offer another demand response event for ventilation. So what that means is we've got about half an hour we can turn off ventilation in the worst space, about 4 hours we can turn off heating or cooling in the worst space, recognizing that that might still be a little bit noticeable for some of the time. So we've got demand response that the building can offer. And we looked at to what extent do all of those loads add up to? And we found that on average, we could offer a turn down service of around 46% of the building energy consumption. Once you take into account how much the heat pumps were using, how much the ventilation was using, we looked a little bit at lighting and a little bit at the lifts as well. A very small amount of the loads in the building require a 5-minute advance notice before they turn off. Most things could turn off instantaneously. And so what this means in terms of the amount of load that we could offer is certainly that it's seasonal, but it's certainly not insignificant. It's not like we're saying demand response for this commercial building is 10% of its load. No, it's more like 45, 46%. And that varies throughout the year. So the right-hand graph is in percentage, the left-hand graph is in kilowatt, and we can get up to 54% of load deferral in the cooling period. And March, my little picture is covering kind of some of my, 40, 40%. Yeah, so March and November were our worst months in terms of only being able to offer 40% of load deferred. But that's really sizable for the local network to be able to come to us and say, can you turn down 40 to 50%, depending upon the time of year? Oops, sorry. So our building is not a fantastic example and really different to other commercial buildings. When we look at the energy demand per square foot and look at typical consumption compared to benchmarks, then our consumption per year, per metre squared of floor area is bang on average. It's bang on average for good practice rather than typical practice, but it's an average good practice commercial building. It was built during 2015-16 and commissioned late 2016, and our first set of full annual kind of seasonal data we took was the 17-18 calendar year for the academic calendar year, so that we could see the pattern of use of the building, because it is a university building. So it's good practice. It is lower than kind of typical. Certainly, it's better than typical, but it's not excellent by any means in terms of its performance. So we feel that this building is a good representation of what commercial buildings could do. It offers substantial flexibility to the local network, and in a way it can be viewed as a virtual power plant, a energy resource that can provide flexibility to the local network. And if you were to provide this same flexibility using a battery instead of a building, then in terms of the amount of kilowatt or kilowatt hours provided that the building can offer, and if you were to look at just during office hours, which is the first few columns in the table, just the office hour provision that the building can offer, we can offer a minimum of 50 kilowatts throughout the year. We can offer an average of 141 kilowatts throughout the year for about 50% of the time. And if we were to look at just the top third quartile of what we can do, then for a quarter of the year, we could offer 168 kilowatts of flexibility. If you were to buy a battery of that size, it costs you £1 million. So instead of the network needing to buy £1 million worth of flexibility, they can use a building that's already built. So we think buildings are an opportunity to offer flexibility. I think that flexibility can stay within the comfort envelope of the occupants. This has given us some really good understanding of how the building system works. It's quite a complicated building because of all the zoning and floor control that we specifically put in there, so we could use it as a bit of an experiment. As a single building, based on current market conditions, it's too small to provide flexibility because markets are such that you have to be quite large to be paid to offer flexibility. But if the university was to add up all its buildings and offer an aggregated flexibility service to the local network, then that would be possible. So aggregation or new market conditions would enable the university to gain some value from this. And we've spoken to aggregators to think about this. So we're interested in active buildings generally at the university. We are convinced that a fabric first passive design is important. The USB is by no means a fabric first building, but it is quite thermally heavy, as I said. So it does have some thermal mass associated with it. Once you've done really well at your energy efficiency and your passive design, the next thing to consider is what's your most efficient system to then provide the energy services that the building does need. What is your best HVAC, heating, ventilation, and air conditioning? What kind of data capture do you need in order to have some good control strategies of that? And then what on-site renewables are possible? What energy storage might be possible? If you've got electric vehicles, what kind of integration could be possible to help, again, the building to offer flexibility? And what does that mean for potential local energy systems like microgrids? We looked at the urban sciences building in the context of Northern Power Grid and the national energy network and the markets for flexibility within that. But microgrids and more localized control could mean quite different market conditions for flexibility overall, which could enable buildings to be much more active participants in future. So that's a bit of a whistle-stop tour of the urban sciences building. The building is a power plant work that we've done, and we're extending that now through a new project called Active Building Centre, where we're looking at these key principles and thinking about how buildings more generally, not just the commercial one-off that we looked at, how buildings in general could offer flexibility services in future to our more active energy networks. I look forward to some questions.
Sarah, thank you very much indeed for that. That was very interesting. It's certainly fueled up a few questions in my head. So before I jump in and misuse the chair's privilege, has anybody else got any questions that they'd like to raise? I'm just trying to work out how best to get the best screen up. Sarah, are you okay to stop sharing and then I can
Certainly.
Do that. Right. So has anybody got a question they want to jump in with? Mark, go.
I don't want to abuse the sort of cheeky board member's privilege and fire in with a question first. But no, Sarah, and I had to nip out at the moment, so I hope I didn't miss it because the rain arrived in Rendell while you were talking. But did you find any evidence from doing that deferred demand of increase or penalty in performance of your equipment? And was that something you were able to take into account while you were doing your work?
This is a really good question, and I got a really similar question when I presented this at another meeting, and that the answer is no. We haven't looked at what the potential O&M impact might be, operation and maintenance impact might be of increased cycling on and off of some of the equipment. We haven't looked at that, but that is something that has been raised previously, and so we should actually try and do some research around that, I think, to better understand the impact on the HVAC systems of increased cycling.
We would certainly be very interested. Declaring interest here for the point of view of being slightly involved with Reflex, but equally in previous projects like Smile, where we're looking to create flexibility for heat pumps in a domestic setting. And we're key to look and see, is there a way that we can actually create flexibility that suits the nature of the beast from the heat pump point of view, as far as duty cycle and things like that goes. So on a smaller scale, we're really interested. But just wondering, because you have even a bigger playground to explore it, I'd be very interested to hear any follow up on that.
Yeah, a couple of questions that I got. I'll since Mark has abused his position, I'll get in there anyway. You mentioned that that this was a pretty good average building, and I wondered how you expected those figures of the rates, or the periods, the length of the periods that you could turn things off for, how they would vary if the building was worse. In other words, would it be generally shorter times in both cases, or is it more likely to be shorter in the summer but not quite as short in the winter type thing? I just wonder if there was any picture about the nature of the building stock, whether that you could infer anything from what you've done there.
Yeah, okay. So in terms of the the heat pumps and the turning off of heating or cooling to the space, then a poorer performing building would see an increased percentage of hourly periods during which the temperature drift would exceed that 0.5 degree per hour. So certainly in terms of the thermal performance of the building, because it was thermally quite heavy, it's got quite a lot of concrete and insulation, then it was slow to heat up and slow to cool down, slow to heat up in summer, slow to cool down in winter. And I think a poorer performing building would see more exceedance of that 0.5 degree. In terms of the ventilation, then our worst performing spaces were already only able to offer a 1/2 hour interruption. And those were spaces where there were no openable windows. In spaces where windows are openable, even if you've got mechanical ventilation, if you offer flexibility by turning the ventilation off and opening the window, then you don't exceed the CO2 limit of 1,000 parts per million. So your building could be really badly performing, but if it's got openable windows, you're going to get enough fresh air. Doesn't necessarily mean it's easy to heat the building with a poor performing building, getting lots of fresh air and air change rates. But from a ventilation point of view, I think so long as a poorly performing building has got openable windows, then that does make a difference. Now, anecdotally, we have another building on campus which is supposed to be fantastic from an energy performance point of view, and it doesn't have any openable windows, and the occupants hate it. There's an element of personal control in space that is still really important for building occupants. And this isn't just about, what can the building do? It's also about how can we make buildings nice places to live and work.
If I can offer a small anecdote, I used to work at the Environment Agency, and in Dorset, we put an extension on the building. So I sort of supervised that. And when we put the new extension up, we got various heat sensors around the building, and we could not get the building heating stabilized because people were coming in the morning, decide it was too cold, and then crank the thermostat wide open on the radiator valves. I'll open it quickly so it heats up quickly. No, it just raises the temperature it'll get to, you idiot. And these were quite intelligent people, but we could get nowhere with it. So in the end, one Saturday, we went round, we set all the thermostats to the right temperature, and then took the grub screws out so that they could fiddle with the controls. Their heart's content, and nothing happened. And the building settled down, and it was fine. And everyone kept fiddling with the controls, and it just worked. So we just took control away. So they still openable windows, but I had a small box of grub screws on my desk. But that was quite effective. So the illusion of control is also quite powerful, let alone the actual control.
Yes, the illusion of control. Rebecca's got her hand up.
Oh, Becky, go.
Hi, Sarah. I wanted to ask, kind of leading on from that, was how, what interaction you had with the building users in terms of feedback, and also what you thought there was in terms of the possibility of working with the behaviours of the people in the building to help see if there's opportunities to add to the efficiency by changing behaviours.
Yeah, that's a good question. So in terms of interaction with the occupants, there was a standard post-occupancy evaluation piece of work done by the design team. And so there was quite an extensive, it's called soft landings, quite an extensive handover period during which the design team were involved in kind of the fine tuning of the building and getting feedback from the occupants. And so that was done over the first 12 months of the building being commissioned. And the feedback from the users wasn't really so much in relation to its comfort thermally or its comfort from a fresh air point of view. There were some concerns about comfort, visually, some issues around glazing and direct sunlight into spaces, which made it difficult for seeing screens and so on. So there were some issues with the visual comfort, more in terms of feedback from users. Our initial work around what happens if the ventilation's off or the heating's off was all simulation until on site there was some construction nearby that caused a trip on the local electricity network. And then our building didn't have any heat pumps working or any lifts or any ventilation. And so what was interesting in that instance in terms of building occupants voting with their feet was that the computer scientists in that building didn't leave until they were told to leave, because it was still operating sufficiently in terms of comfort. Yes, they, you know, and if they weren't on laptops, then they didn't have an opportunity to actually physically work. But in terms of the building being comfortable enough and being able to open windows for fresh air, they were quite happy with that. It was a health and safety decision by estates that meant that people were told that they had to leave the building, rather than people going, right, it's too cold now, because it was in winter. So yes, it's been a really interesting building to look at, because it's got the heating load and the cooling load, which means that there's some opportunity for year-round flexibility to offer to the local network that's been useful. In terms of future interaction with occupants, it's quite limited. There's no ongoing behaviour projects at the moment. We've put some bids in for some, but haven't yet been successful. So I saw this lovely idea that they've done in the States, where they've got this display as you come into the building, and which is a screensaver on all of the building computers, which is a aquarium, and the health of the aquarium goes down at times of high demand in the building. So you can actually kind of visually see something that represents the building energy use. And so we wanted to do a bit of a experiment with that, but we haven't got the funding, but we'll push on. We'll still try and get some behaviours happening there.
There was a board member who's, oh sorry Neil, I'm just
I was going to ask you, invite another question, go Carol.
No, I was going to say there's a board member who's not here who actually wanted to put a big like arrow in the middle of Stromness for the same reason, from that point of view, and just saying how much we use more or less for that point of view. I think yeah, we know he's not here. Dave, I think Dave has a supplemental. I had a supplemental, but I'll let Dave go first, because I'll talk too much otherwise.
But you see, I've got 3 questions, but I'll spin them out. I'll just do one to start with. So if you switch off your electricity, then the electricity company get a free ride for a bit. But isn't there a penalty after that you then have an increased demand afterwards? So you're offering deferral, but then you're going to ask for an increased demand half an hour later.
Yeah, and we had a really interesting discussion with the estates team on this, because our modelling showed that you didn't have to. So say your air handling units were running at 80% most of the time, and then you turn them off. And so when you turn them back on, they had to be at 100% to catch back up and get you back to comfortable levels of CO2. What we found was that you were still net electricity wise better off. And so the sustainability team were like, well, why don't we just turn the building off for periods of the time that no one notices in the building, and we save a bit. Even if we don't get paid to do that, ultimately we use less electricity in total. And so the building was able to respond and catch back up in a way that didn't lead to net increase in electricity demand. We had a net saving in electricity demand during those simulations of what would happen.
Yeah, okay, so that's I'll press on with question 3 here, because you really touched on that. And that is, do you think it's a better strategy to act as a store, which is what you've been talking about, or just to look at all the levers you've got and go for minimizing the total overall demand. So, for example, your CO2 level, just turn the fans down and down and down until you hit 1,000.
So if you're running some of your systems on part load, you're not necessarily operating at best efficiency of those.
Yeah. Okay.
So that is something that you would need to take into consideration. But in terms of whether it's better to act as a thermal store or whether it's just better to minimize your own electricity demand, that depends on whether there is any market for being a thermal store. At the moment, for this building, there is no market, so we wouldn't get paid for doing any of the flexibility. It would be a favour to the local network. Whereas if there was an aggregator who was adding up lots of flexibility from lots of providers and could get to the minimum requirement for the market entry, then we could get paid as one of the services that the aggregator provides. So it's only beneficial to be the thermal store if you get paid for it.
Can I just chip in another point there, Sarah? And I wondered, because given the cost of electricity, the price on that changes, and the spot prices will be changing on a sort of half-hour basis. I suppose one of the other advantages of turning the building off for an hour now is that this is the most expensive time, and we'll just run the fans in an hour's time when the price of electricity has dropped off a bit. So there's a further, it's not actually being paid for that, but it's a further potential saving that you're just avoiding the peak electrical demands and therefore the highest price points for the electricity you're buying.
Yeah, and that's the kind of service that we're looking at as part of the Active Building Centre project. It's not necessarily getting paid to offer the flexibility service, but getting incentivised to offer it through a time of use tariff.
Because once again, so there's two parts to that, isn't there? There's actually the units cost less, but also if the utility company knows that they can boot various people off the network, they don't have to reinforce their network, and therefore they make a saving in their investment costs. And so they'll pay for that service for you to be willing to be flexible. So that's,
yeah, well, I think you sort of suggested it yourself there, Neil, that all you really have to do is advertise the price at half-hour intervals, and let the computer in the building say how am I going to optimize how am I going to minimize my cost today, and you don't need to then aggregate with anybody else. You'll just modify the behavior of buildings across the UK.
Or potentially do both if they are in the same direction. Yeah.
okay, Mark, you were going to. You had another point.
Well, no, I'll let Michael go. Some partly as well.
I can't see any hands up here, so I'm missing this. But anyway,
Keith is waving and Michael is waving.
Okay. So Michael first, and then Keith. So sorry about that if I'm screwing this up, everybody. Keep going.
Michael, you're on mute.
Mute. Right, I'm off mute. Thanks, Neil. Yeah, Sarah, that was really interesting. I think what Mark touched on before about our interest in heat pumps on a domestic level, we're looking for data. I say we, Home Energy Scotland, and the job I do, we're looking for in situ data for heat pumps. And you mentioned it wasn't an air to water heat pump. I'd be interested to know what it was, what type of heat pump. Do you know what the efficiency of the heat pump is, and what the emitter, which obviously gives off the heat in the building?
So the easy answer to that is no. Yeah, if you were asking Mohammed, he would just go like that and tell you what the heat pump manufacturer is. But I don't know off the top of my head, but I can find out for you. Yeah, I wouldn't like to guess. I think they're Hitachi, but I'm not sure. So I can find out and confirm the efficiencies.
Yeah, it's more the efficiency of it as opposed to the model. And what heat emitter is in the building? Is it underfloor heating, or is it? I take it it's not radiators in that building.
It's not, no. So it's it's radiative panels that are suspended from the ceiling. Again, I would have to go away and double check how those are linked up with the wet system, because it is all a water-based system internally.
Okay. Yeah, I think again, from our point of view, on a domestic level, we've always felt, you know, turning heat pumps on and off is not the most efficient way. I think that's been touched on here in some occasions. I think what yous have shown that there may be some scope for it, but I think it's finding out whether we're comparing like for like, because it seems like obviously there's more going on in the building you've got than what we see on a domestic level. But no, it's interesting. There's lots of work going on at the moment trying to find out, you know, the best way of running heat pumps and the efficiency of them, and hopefully we'll find out sooner rather than later. Okay, cheers.
Thanks, Michael. Keith, do you want to come in?
Yeah, it's when you were doing your research, Sarah, were the number of bodies in the building constant? And did you ever look at increasing the number of bodies per square meter within the building to see if that made a difference?
So the number of bodies in the building does vary throughout the day as well as throughout the academic year, because it is an academic building. And the variation is most significantly reduced, i.e. the numbers are at their absolute lowest over Christmas. We do have quite a number of PhD students and researchers that still come in over the summer. So unlike schools, we don't completely shut down as a university. You have a kind of holiday allowance that you can take at any time when there's never a quiet time of year. But the undergrad students are in from September through to about May. And so the lecture spaces and the teaching rooms are very heavily used at those points. But the office spaces, the meeting spaces, they're used throughout the year, as are some of the student spaces for the PhD students. The only quiet time that we find in terms of the demand is at Christmas. We do see a reduction in demand in the building overall at weekends compared to weekdays. And summer is a little bit like a weekend all the time in terms of the building demand in total. But the occupancy, yeah, it does vary quite a bit throughout the year because it's a student-facing building. So you asked me, did it vary? Then you asked me another question. I can't remember what it was.
Did you look at increasing the number of bodies per square meter within the building at any point?
No. So what we did was we modeled the spaces according to their design limitation. So for that particular type of space, then what was the design occupancy? And then we modeled that. Now, that particular space might get overused and there might sometimes be more people in there than we have modeled, but we modeled the design occupancy.
Okay, thanks.
Okay, anyone else will come in with another one? I've got one. If you're going to do it again, what would you change?
If I was going to do it again, I would definitely involve the O&M manufacturer who installed all of the sensors. So what we found with the sensors was that some of the labels weren't very clear as to physically where they were in the building. Some of the sensors, we had to identify when they had last been calibrated because they didn't seem to be correctly measuring. And certainly in terms of the volume of data that we had and where that was stored and how it was accessed, those elements were actually the hardest bits of the project, because we really needed that data to validate our model so that we could then use the model to investigate scenarios that hadn't yet happened in reality, like turning the ventilation off or turning the heat pumps off in the middle of summer and not offering any cooling. So the data was really important to validate the model and make sure it was reasonably accurate. And it was all around the data that was the biggest headache for us. Now, ironically, we are part of a initiative called the UK Centre for Research Infrastructure. And this is an initiative that set up a number of urban observatories. So we have an urban observatory at Newcastle. That urban observatory has live streamed data that goes to it. So we've got data scientists that know how to do this stuff. But it's still not easy when you give the commissioning to someone else. You give the sensor specification to someone else. You ask them to do all of the installation, commissioning, calibration of all of those sensors. And all you do is sit there with this lovely database that all of this data drops into. Because when that data doesn't drop in or doesn't look right when it drops in, there's this void of expertise that you're missing. So from that point of view, I would have wanted to include those more significantly, I think, in the project up front. We did have a project advisory board that included the architect, because they were really keen to learn what could they do better on the next building, particularly if buildings are going to be more flexible. We had the council on an advisory board who were really interested in what they might be able to do with their buildings. We had Siemens on the advisory board. They provide the building control for that particular building and others for the university. And they were quite keen on, what control architecture could future buildings need. So everyone was really keen to learn, but we didn't have the sensors people on that. And that was a gap for us, the sensors.
That's really interesting. I see Alistair Morton's lurking in the background somewhere with his camera off. Alistair, had you got any thoughts about that, given how much you put in terms of the council's building control stuff?
Yeah, I feel your pain as far as the controls goes, and that's always an issue that we have is trying to get everything commissioned up at the end of the project, and it can be months into the project before you realise that the data you're getting through is nonsense. So I do understand that. One of the things I was interested in was obviously in the ventilation. Our ventilation is going to become a major issue in buildings over the next few years, I would think. And obviously there's big savings to be made by turning ventilation down. But I think it's the fan laws are, the power is the cube of the volume that's going into the building. So if you can reduce the volume just a little bit, you can get big power savings. So I was wondering if you'd looked at just reducing ventilation rates rather than switching off entire systems.
We haven't done no, but we have quite an interest from another professor who is looking at privacy issues. And so we had this idea of, well, if you know how many occupants there are in the building and where they are, maybe you could target the ventilation. But this is a kind of security and privacy issue around monitoring who is in the building, when and where. And so it was quite interesting to have her input into some of those discussions we were having as a potential follow-on to think about how could you target some of these issues. And certainly the initial discussion came about in terms of the 2 meter spacing and then 1 meter physical spacing for COVID restrictions, and how would we know how many people were in the building, and therefore what the average floor area in between people was. And we don't have a way of monitoring people coming into this particular building. We know if a space is occupied or not, but not how many people are occupying that space, only if it is occupied with occupancy sensors. And so that led on to some discussions around ventilation, but at the moment we don't have a solution to that, and we haven't investigated the potential for part loading or zonal loading of the ventilation. We know we can control it that way because that's the way the building was set up zonally, but we haven't got a way of knowing whether certain spaces are more or less occupied to be able to reduce ventilation to that space.
And just your environment sensors don't give that granularity on the CO2 and the temperature, which would be an anonymous way.
The CO2 and the temperature, you can try to infer occupancy from that. And so we did a little bit of a study. So in some of the spaces, the students have to scan in and out with smart cards to access particular learning spaces if they're in a lecture theatre or in a computer lab. And so we thought that would be a good proxy to tell us exactly how many are in there, how quickly does the CO2 rise before the ventilation kicks in, and then your ventilation doesn't tell you anything because it's refreshing so quickly that you can't infer occupancy from CO2, and also looking at temperature. And it became very difficult to be able to predict occupancy from temperature and CO2 because the HVAC was switching in and reducing the CO2. So CO2 didn't become a good proxy of occupancy. So we're still looking at that and trying to understand what other environmental factors could be a proxy for occupancy. And we're using a machine learning method called transfer learning. So if this particular space has this particular temperature and CO2 with 2 people in, and this space has this CO2 and this temperature, then what occupancy might that infer to try and transfer the learning from one space to another? But it is quite difficult when you've got mechanical ventilation because CO2, once the ventilation kicks in, doesn't become a proxy for your occupancy, if that makes sense.
Yeah, it does, but I might be being dumb, but is there a reason to be your control to be led by occupancy rather than environmental condition? It's
led by environmental conditions. So as soon as it hits 1,000 parts per million of CO2, then the mechanical ventilation kicks in. So whether that's 6 people in a space or 1 person in a space, once the 1,000 kicks in, then the ventilation is switched on. That's the threshold for the control.
Yeah, so that's the end of your deferral period, the end of your flexibility in that sense. Rather than whoever it was earlier, was it Keith talking about could you maximize for a certain CO2 level or something? Okay, yeah, I'm with you. Yeah.
Okay, anybody got any other questions? Say, because I can't necessarily see unless you've got your camera anyway. Oh, Dave, go ahead.
I was wondering, you plan things so that the people in the building would never notice what you were doing, and I was wondering whether, in general, we treat people in offices too well. And I mean, if you go to a pub, you expect it to get hot, and that's just life. And I just wonder, are we putting a huge amount of energy into buildings to keep everything perfect, rather than saying to people, put on a jersey and or take your jersey off because it's getting hot?
So yeah, the easy answer is yes. Our heating and cooling set temperatures are set regardless of what the outside condition is. So you've got a kind of fixed thermal comfort approach to that, whereas adaptive thermal comfort is an approach where it says your inside temperature should be, 4 degrees more than your outside temperature. So as your outside temperature changes, so does your inside temperature, in order to reflect the fact that your thermal comfort can adapt to an indoor environment that better reflects the outdoor environment. And so adaptive thermal comfort might be the way to go. Our thermal comfort theory is all based on tests done in the 1950s on male soldiers. So it doesn't it doesn't reflect potentially thermal comfort for females. It doesn't necessarily reflect thermal comfort in modern conditions with different clothing levels. It doesn't reflect thermal comfort in different cultures with different clothing levels either. It's a very westernized theory, Fanger's theory of thermal comfort. So there's definitely more we could do to have a thermal comfort approach that better reflects local conditions and local cultures.
Well, what I'm suggesting is a thermal discomfort rather than saying, no, you're going to be comfortable all the time.
Yeah. Well,
you're paying for this. No, you're going to have to put up with some of the pain here. Yeah.
So Mohammed loves this idea, and the idea is that if you lower internal temperature in certain circumstances, obviously it's not right for everybody, but actually there is some evidence that physically that is good for you.
Yeah, yes, yes. If you're trying to do some work, yeah, quite right. Yes.
Interesting.
Good point. So you might actually increase productivity by turning
keeping people cold.
Save money. That's right. Yes.
Shush.
Okay. The other thing that occurred to me was that you've probably heard about this as a strategy for cold stores, that if you know you're going to have a peak demand and you want to turn off, you can run the cold store a bit colder so that you can turn it off for longer. So you could do that with your building as well. You could make it hot because you're going to have to turn off.
Yeah. We didn't look at that, but what we did look at was making sure that in the 4-hour period for the heat pumps, when heating or cooling was turned off to the space, for that 4 hours, would we still be within the comfort band that the building control system was set to? So we didn't try and say, okay, we're going to turn the cooling off in a minute, so let's cool down to 16 instead of having it at no cooler than 18. And then allow it to warm up. We didn't model that.
Mark, it looked like you were trying to get in with something again.
No, I am, but Michael's got his hand up again. I don't think he's
I can't see. Don't ask me.
It was just a short comment on most heat pumps now have weather compensators where they will track the weather, the outside temperature. But on a more sort of light-hearted note, just as an anecdote, I'd done a recent visit to a household in Caithness, and it was a pensioner household, and she said to me she brings the girls in during the winter. So I obviously asked her who the girls were, and it was 2 Shetland ponies that she brought into the kitchen, and she kept them in the kitchen during the winter months. And she said, well, it's a great way of warming me, 400-pound animals. So I just wonder whether doing your occupancy assessments, whether it took into account Shetland ponies.
We didn't model computer science students as Shetland ponies, to be fair, but we did model the passive gains that you get from people and from equipment.
Cool.
But no animals were harmed in the making of this research.
Thanks.
Mark, did you want to come in?
No, I'm conscious of time. I mean, I've got about 3 or 4 other questions that are tied in with some of what people have said. I suppose one of the most interesting ones was tied in early on, almost with what you were saying, Neil, that it's that difference, and sometimes it's a good thing and it could be exploited, and sometimes it's a worry. It's people's perception of comfort compared to the reality. And you talk about relative temperature change and things like that. So from Dave's point of view, what you can get away with in a building if it happens slowly. But then also seeing the other side of it, and Michael would agree more, and having the other more serious situation, poor housing, where people get into thermal death, but to some degree almost that situation, because they actually go down lower and lower, and making sure we're safeguarding against that. And I just wondered if the building there was an opportunity, as Neil was saying, is taking his grub screws out, that because also if you do an active survey, people say, oh no, it was fine and all the rest, but it's picking up those indirect signals, like someone reaching for a thermostat and tweaking it, and someone opening a window, and getting that data set to give almost a true reflection of people's comfort, because I think it's quite hard to get it actively. That was it.
Yeah, and I think the best way to do that is perhaps through diaries, but a little while ago I did supervise a student who was looking at thermal comfort in care homes, because as you get older your thermoregulation isn't as good, and so it was quite interesting to see some of that research about the risk of overheating in care homes, and the occupants weren't necessarily recognizing that they were feeling too hot, because to them their thermoregulation isn't as sensitive as you get old. So that was quite interesting to consider. Obviously we don't have as many old people in the computer science building with some students there, but you know, that's why I think thermal comfort needs to account for local conditions, for culture conditions, and for the occupants themselves. It can be very different to an average person. Yeah.
And even ventilation and boundary layer effect and things like that becomes significant.
I can offer one final anecdote. When I used to work at Christchurch Borough Council, we moved into this new office block. It was reasonable for its time and double glazed and various things, but it was 250 people in it, and it had one temperature sensor in it. And that was actually up in the Chief Executive's department. And one of my colleagues who sat in an adjacent section of the drawing office, his job was trying to sort the building maintenance side of things out and trying to get things balanced. And he could not get the building to settle down because everybody was complaining that this floor was too hot and that floor was too cold and couldn't work this out. He eventually traced what the problem was. And it turned out that there was one of the secretaries in the Chief Executive's department, a young woman, who didn't actually wear much clothing, to be brutally honest. And she was sitting in front of the temperature sensor. And she found the building was too cold, so she put a hot air heater under her desk. And that was blowing on the wall and then blowing up against the temperature sensor. So the building thought it was hotter, and therefore the building turned itself down and everybody got colder. And we moved her desk and the problem solved. So I never underestimate the human factors. That's my point. So it's just never. So. Anyway, has anybody got anything else to ask Sarah while we have her? Because if not, and if anybody can see anybody else waving, because I'm seeing no clues about hands up on this one, but we'll talk about that later. If not, I'm going to say, I'm going to draw this to a close and say, Sarah, thank you very much indeed for giving up your evening for us this evening. That's been absolutely excellent. We've really enjoyed it. Learned an awful lot about things, and I'm very envious of the scale of the data capture you've got. And I'm sure Alistair probably isn't. He's pretty teary, little hairy, having 337 zones and 15,800 data streams. So we've got enough trouble as we've got at the moment. But you know, seriously, thank you very much indeed for all the work you're doing on this. It does sound really interesting. If there's anything that you think we can do at any stage, we're a group of people who are interested in trying out new ideas and trying to work with different things, and we're always interested. So if you do learn some other great insight, don't hesitate either to let us know and come back and tell us something else, or similarly, if you think we can help in any way, then don't hesitate to pick up the phone and ask. So we owe you one. So there we go.
Thank you very much.
So thanks much indeed. Thanks everybody for attending this evening. I hope you've enjoyed it. Next one will be on whatever it is, the first Tuesday of next month. No idea what it is. I should have got the program organised, but I forgot. So there you go. So keep your eyes on the press and Facebook and all the usual channels. And otherwise, thanks much indeed, everybody, and have a good evening.
Thank you,
Neil. Thanks, Sarah.
Thanks, Neil. Thanks, Sarah.
Thanks, Sarah.
Thanks.
Thanks, Mike.
Yeah, I'm never just very sure of the etiquette at the end of these meetings, whether you should just cut everybody off completely or wait
No, I
till they
don't.
go themselves.
I've had those ones where everybody just gets booted out of the meeting in a one and go, oh, that's it then, fair enough. Super. Thanks, Ashley, for that.
The hands up, by the way, if you look at your participants, then you see the hands up in that.
Oh, I had a look and I couldn't see that. So,
it's showing up on mine. Maybe it only shows to the
so
host.
all I've got in participants is invite. That's the only thing I've got.
You're not seeing you and me in it?
No, I'm seeing participants 2.
Yeah.
Hold on. If I click on participants,
Yeah.
it then brought up the list of participants on the side. But when I just had the button at the bottom saying participants, if I hovered over it, the only thing, or there's a little up arrow in the corner, participants, and all that does is bring up the word invite.
Oh, right. Yes. Yes. No, you have to
So-
click
so
on
I-
actual participant.
Right. So,
And you can also drag that out to the main screen if you want to put it somewhere more convenient.
right. Okay. No, that's fine. That's what I wasn't doing. So thanks for leaving that. Good. Thanks for that, Mike. Are you okay to transfer that over to me at some stage when it
Yeah.
serves?
You just want it to send to you, or?
Yeah, that'll be fine. Or even if you send it to OREF, you send it to Frances, that'd be fine. She could put it up on the site in due course.
Yeah. Well,
So-
the stuff I did some stuff before and I sent it to her. I thought that
Oh, that's great.
she
Yeah,
does the website, doesn't she?
Yep, just the job. Thank you, Mike. Thanks very much indeed for that this evening. I really appreciate it. So
No problem.
I'll see you at the Science Festival thing very soon, I assume.
Oh yes, of course. Yes, that's coming up.
Coming out at a great rate in lots, isn't it? There you go.
Yeah.
All right. Have a good
Okay
evening,
then.
mate.
Right
Cheers.
then.
Bye.
Cheers.
Bye. Bye.